This Zoom session is being brought to you by the Fractal Globe Snow Ring W. All right. For today, we'll move on to a little bit about vectors. And it has a little bit of trigonometry connected to them because there's both rectangular and polar coordinates for vectors. A vector, think of it as an arrow in space. It's a displacement between 2 points. Here's the initial point arrowing over to the terminal point. We consider vectors equal if they have the same length and the same direction. Just a moment. So for example, here are two vectors with different lengths, so they're not equal. Here are two vectors of the same length, but different directions, so they're not equal. Here are vectors, same direction, same length, different places, different initial and terminal points, but they're the same displacement, so they're the same vector. All right, given a vector in the plane, it has a rectangular x component and a y component, and it's written therefore as v equals a by b with these little angular brackets around it, sort of like point notation, a little different because they're not quite the same thing as points. If you have a vector from x1, y1 to point x2, y2, then as a vector, it's x component is x2 minus x1, the change in the x values, and its y component is y2 minus y1, the change in the y components. Given a vector, it'll have a length, vector a by b, its length can be thought of from the Pythagorean theorem. It's the square root of a squared plus b squared. We denote it by this double line, sort of like an absolute value sign. Now, vectors have an arithmetic. You can add, subtract, and multiply. If you have two vectors v and w, before I go on, let me see, did I mention this? I did not. I really should have said this way back here. Because it's a displacement between 2 points, it's useful in many branches of science. In physics, in physics, a lot of, and engineering, it can be thought of as a displacement, or as a velocity as a vector, or an acceleration as a vector, or a field as a vector. So it's all over the place in physics. All right, given two vectors, v and w, you place them with the same initial point. At the terminal point v, you put a vector w. At a terminal point of w, put a vector v. They should wind up pointing to the same point, and you get this figure, which is called a parallelogram. And then the displacement from the shared initial point to the final the shared terminal point, that's the vector u plus v. Now, it turns out that that's the geometric version of adding vectors. The algebraic version is you add components. A by b plus big A by big B is A by big B plus big B. So you add x components and you add y components. You can rescale, okay, and of course you can subtract vectors. A, B minus big B is A minus big A, B minus big B. Given a vector v, twice v is in the same direction, twice as long. A half v is the same direction, half as long. Negative v is the same length, but the opposite direction. And so on in general. You can multiply a vector by a number. And that's how it is geometrically. Algebraically, you multiply both components. K by the vector a by b equals ka by kb. Now, these vectors are defined in terms of addition and multiplication, and they have many of the same laws as numbers, addition, and multiplication. For example, order doesn't count. B plus u equals u plus v. That's a cumulative law like in arithmetic. U plus v plus w equals u plus v plus w. That's the associative law, same as in arithmetic. There's a special vector 0, which is 0 by 0. It's a vector of 0 length. It'll look just like a point, which is a displacement which doesn't displace at all. And u plus the 0 vector equals u. And given a vector and its opposite, they add up to the 0 vector. The associative law also works for multiplying vectors by scalars. K times u plus v is ku plus kv. Basically, if you take this this diagram here and you make it twice as big, then you get 2v plus 2w equals 2 of u plus v. And it's associative for multiplication by a number. K times h equals kh times u, where k and h are numbers and u is a vector. And it is also distributive over number addition. The number k plus h, that times e equals the vector ku plus the vector hu. Now there are some special vectors, 1 by 0 and 0 by 1. The 1 by 0 vector is in one unit in the x direction. The 0 by 1 vector is 1 unit in the y direction. The 1 by 0 vector also goes by the name I, with this little arrow above it. It's traditional to put a little arrow above a vector name. 0 by 1 is in the y direction is the vector j with an arrow above it. And if you have a by b, then it's easy enough to prove that it equals ai plus bj. You break into a by 0 plus 0 by b, and that first one is a times I, the second one is b times j. So you can write any vector in terms of a combination of I and j vectors. Now, and that is, of course, rectangular coordinates for vectors. But there's also polar coordinates. Given a vector v with a length, with a vector length, and at an angle theta from the positive x-axis, then the vector v will be length of v times the vector cos theta by sine theta. This is the length of the vector. This cos theta by sine vector is the vector of unit length in the v direction. It also equals v over its length. And this is a lot like what we had the other day about writing a complex number in polar form. R cis theta. This is a lot like it. Okay, now, so we have some examples. Here's a vector with length 14, and it's 120 degrees from the x-axis. What are the components? All right, here we go. The vector v is a length times cos theta by sine theta. That's 14 times cos 120 by sine 120. That's 14 times. Okay, you can check it out. Cos 120 degrees is -1/2. Sine 120 degrees is √3/2. And then if you multiply both of these components by 14, -1/2 times 14 is -7. √3/2 times 14 is 7√3. So -7 by 7√3, or in other words, -7i plus 7√3j. So that's the rectangular version of this in polar coordinates. Here's a vector from the point -2 by -1 to 6 by -2. What's the vector's components? Well, terminal point minus initial point. 6 minus -2 in the x component. -2 minus -1 in the y component. A bit of arithmetic. The vector v is 8 by -1. What is the length of the vector 3i minus 4j? Okay, well, 3i minus 4j is a vector 3 by -4. Its length is square root of sum of squares. Root of sum of 3 squared plus -4 squared. That's root of 9 plus 16, which is root 25, which is 5. This is the 3, 4, 5 triangle. What's the length of the vector I minus j? Well, I minus j is a vector 1 by -1. Its length is root of the sum of 1 squared plus -1 squared. A bit of arithmetic, that's the square root of 2. Now here's a curious one. Here's the vector 3 by -5. Here's the vector -2 by 3. What's 2v plus 3w? What's the length of v minus w? And slightly different, what's the length of v minus the length of w? This is a definite case where order of operations counts. He would take the subtract and take a length. He would take lengths and subtract. All right, starting with this, 2v plus 3w. So okay, here's v, here's w. 2v plus 3w is 2 times v, 3 by -5, plus 3w is 3 times -2 by 6. Okay, multiply 2 times 3 and 2 times -5 is 6 by -10. 3 times -2 and 3 is -6 by 9. Add them by adding components. 6 plus -6 is -6. -10 plus 9. Okay, 0 by -1, and that's the vector -j. Length of E minus W, that's the length of 3 by -5 minus -2 by 3. If we take differences of components, 3 minus -2 for the X component, -5 minus 3 for the Y component, that's the length of 5 by -8. All right. Root of sum of 5 squared plus -8 squared. That's root of 25 plus 64, which is the square root of 89. And there we stop. Length of E minus length of W. Well, okay, length of 3 by -5 minus length of -2 by 3. Length of 3 by -5 is root of 3 squared plus -5 squared. That minus. Length of -2 by 3 is root of -2 squared plus 3 squared. So, bit of arithmetic. Root of 9 plus 25 minus root of 4 plus 9. So, root 34 minus root 13, and okay, it's easy enough to check that these are not even close to the same. So these are not the same. Order of operations counts. Now here's a curious one. This will actually force us to do some linear algebra. Oh no, not this one. But here we go. 63. Here we have a vector length 25. Its angle from the positive x-axis is 330. So it's most of the way around. What's its components? All right, here we go. Let V is length 25 times cos theta, cos 330, by sine theta, sine 330. 25 times, okay, cos 330, root 3 over 2, sine 330, -1/2. 25 times each of these gets you 25 root 3 over 2 by -25 over 2. And that's the answer. Now here we have a somewhat more, very much more of an applied problem. Here we have a ton of 1,000 pounds weight hanging from 2 cables. One is at 25 degrees down from the horizontal. The other is at 40 degrees down from the horizontal. What's the force on the first cable and what's the force on the second cable? Now, okay, you write a force diagram. Here's 3 forces, F1, F2, and the weight. F1, okay, it's going up upper left at an angle of 25 degrees. F2 is going up to the right at an angle of 40 degrees, with lengths F1 and F2 respectively. And this 1,000-pound weight is a force downwards, whose components are 0 by -1,000. Now, if you have 3 forces operating on something which is standing still, then the total force must be 0. That's because we have, if there were a non-zero force, then that weight would start to accelerate in the direction of the force. But since it's not not moving, the forces add up to 0. And let's see, F1. Well, okay, 25 degrees to the left, that means 155 degrees from positive x-axis. So F1 is F1 cos 155 by F1 sine 155. F2 is at a length of F2 with an angle of 40 degrees from the x-axis, positive x-axis. So F2's components are F2 cos 40 by F2 sine 40. F1 plus F2 plus 0 by -1,000 is 0. That's because it's at static equilibrium. So F1 cos 155 plus F2 cos 40 plus 0 by F1 sine 155 by F2 sine 40 plus -1,000. This is equal to the net force 0 by 0. All right, now these 2 vectors, these 2 components equals these two components. F1 cos 155 plus F2 cos 40 equals 0. F1 sine 155 plus F2 sine 40 is -1,000. It's positive 1,000 because minus 1,000 is 0. All right, this is a 2 by 2 system with variables F1, F2, and F2. And after much calculation, we get that F1 is 845.2 pounds and F2 is 1,000 pounds. Curiously enough, this force here is the same as the magnitude as this force here. Curious. Okay.